What lurks in a black hole? Scientists have found something unthinkable in a black hole, and its ramifications are terrible. This mind-rending revelation is illuminated by astrophysicist Neil deGrasse Tyson. What caused scientific shockwaves? We'll explore black holes' astonishing, baffling, and spine-chilling secrets. Prepare to be awestruck and have your understanding of the universe challenged. Will you face the unknown? You were in outer space when a horrible accident occurred to you. Because the Earth is a sphere that orbits the Sun does not in any way literally rise. Instead, it is simply the case that you are located directly on the moving line known as the terminator, which divides the illuminated portion of the planet from its dark side. Even though this is true for the entire idea of space travel, the one aspect of it all that has always been exciting and terrifying at the same time has been black holes. The perils that lurk within the great expanse of space can be frightening, and while this is also true, it applies to the entirety of the concept. Black hole discovery. Neil deGrasse Tyson, a renowned astrophysicist, has just lately disclosed a new discovery concerning black holes, which has caused shockwaves to travel across the scientific community. In a series of lectures and interviews, Tyson presented strong data suggesting that contrary to what was previously believed, black holes may not be the ultimate endpoints of matter. The findings of Tyson's research indicate the possible presence of a phenomenon that is referred to as a quantum evaporation. According to this idea, over unimaginably long stretches of time, black holes eventually release particles and energy back into the cosmos. This process calls into question the widely held belief that black holes are unbreakable enigmas from which nothing can ever emerge. The results of Tyson have sparked a great deal of interest and speculation, since they not only call into question previously accepted models of black holes, but also have significant repercussions for our comprehension of the cosmos as a whole. The finding that black holes might have a finite lifespan opens up a whole new arena of possibilities for cosmologists and astrophysicists. This revelation sparks new routes of inquiry and reframes our knowledge of these mysterious cosmic entities. Creation of black hole. The catastrophic collapse of huge stars can result in the formation of black holes, which are fascinating cosmological entities. After a large star has used up all of its nuclear fuel, the core of the star will no longer be able to withstand the outward pressure caused by the fusion events. This pressure is ultimately overcome by the force of gravity, which results in the core collapsing inward. During the process of the star's collapse, its stuff will become extremely dense, which will result in a powerful gravitational attraction. Within a particular boundary known as the event horizon, this gravitational pull is so powerful that nothing, not even light, can evade its grasp. Beyond this region, the gravitational attraction becomes limitless, marking the point at which it is no longer possible to turn back. As the collapse continues, the center of the star will eventually condense down to a singularity, which is a point that is infinitesimally small. It is a region that defies the physical rules we are familiar with, since it has an unlimited density, yet no volume at all. The region immediately adjacent to the black hole has a curved shape, giving it its characteristic appearance. Black holes are fascinating astronomical phenomena, and research into them yields important insights on the character of gravity and space-time, as well as the limits of our current comprehension of the cosmos. Structure. Black holes are mysterious heavenly bodies that are recognized for the massive gravitational force that they exert. As a result of this force, black holes function as cosmic vacuum cleaners from which nothing, not even light, can escape. These gravitational powerhouses come into existence when huge stars disintegrate under their own gravity, resulting in the formation of a region of space known as a singularity that has an infinite density. The tremendous gravitational field that surrounds a black hole forms an event horizon, also known as a point of no return, which is the boundary beyond which anything that falls in will be permanently trapped. The theory of general relativity, which was developed by the physicist Albert Einstein, was the first to suggest the idea of black holes. Although they are not visible to the human eye, black holes can be identified by the effects they have on the material in their immediate surroundings. An accretion disk is formed when gas and dust fall into a black hole in a spiral pattern. As the gas and dust heat up due to friction, they they release intense radiation. In addition, the gravitational attraction of a black hole can warp light coming from faraway galaxies and stars, producing fascinating optical effects such as gravitational lensing. Black holes continue to be a topic of intrigue and investigation because they provide important new insights into the basic properties of space, time, and gravity. Size. Black holes have a surprising range of diameters. Stellar and supermassive black holes are the main classifications. Massive stars explode furiously in their final moments, creating stellar black holes. After exhausting its nuclear fuel, this sort of star collapses under its own gravity, forming a thick core. The star collapses into a stellar black hole when its core mass exceeds the Chandrasekhar limit. These black holes have masses from a few to 100 times that of our Sun. Most galaxies have supermassive black holes at their centers, including our own. These dark holes devour everything. Titans are hundreds, millions, or billions of times heavier than the Sun. Supermassive black holes are believed to form through mergers with other black holes and matter accretion over cosmic timeframes. Astronomers and physicists study black holes to learn about gravity, space, and time in the farthest regions of the universe. Findings. There is speculation that black holes house singularities, or regions of infinite density. According to general relativity, black holes are formed when enormous stars collapse under their own gravitational force. The singularity at the center of these black holes is a region of infinite density and zero volume. Existence in a singularity violates the known physical laws. Extremely powerful gravitational forces cause warping of space and time. Since matter and energy within the singularity would be infinitely squeezed, all known physical rules would likely fall down. Our existing understanding of physics is unable to explain what happens beyond this point because of the severe conditions within singularities. To accurately characterize the behavior of singularities, it is generally agreed that the laws of quantum gravity, an as yet undeveloped theory unifying general relativity with quantum mechanics, would be required. Research into the nature of singularities and the inner workings of black holes continues to this day, pushing the bounds of our understanding of the cosmos and physics. Loop quantum theory. The singularity problem that arises when fusing Einstein's general theory of relativity with quantum mechanics may be amenable to a solution thanks to loop quantum gravity. Physical qualities like space and time, according to the theory, become discontinuous and quantized at the smallest scales of space-time, forming a network of interconnected loops. In loop quantum gravity, these loops stand in for quantized units of space-time geometry and characterize the gravitational field. Singularities, like those in black holes or the Big Bang, can't happen because of this structure's distinct nature. The idea proposes that, instead of collapsing into a singularity, space-time bounces or transitions from a collapsing state to an expanding one, avoiding infinite density or curvature. Because mass and energy cannot be concentrated into an infinitesimally small point where the normal laws of physics break down, loop quantum gravity allows for this resolution. Instead, it sheds light on the character of singularities and the early cosmos and gives a consistent framework for characterizing the behavior of space-time at the quantum level. Types. There are many different kinds of black holes in the universe, each with its own peculiar attributes and history. Stellar black holes are created when stars with masses 3 to 10s of times that of the Sun collapse. Their enormous gravitational attraction causes their event horizon to confine anything that enters it. Black holes with intermediate masses are between those of stars and the supermassive kind, and their existence is shrouded in mystery. Their beginnings are a mystery. However, they may have resulted from the fusion of smaller black holes or their direct collapse of enormous gas clouds. Galaxy centers are home to supermassive black holes that are millions or even billions of times more massive than our Sun. They play an important role in galaxy evolution and in shaping the structure of galaxies. The steady accretion of mass and the merger of smaller black holes is how scientists theorize they originate. Black holes with a net electric charge are called charged black holes, or Reisner-Nordstrom black holes. The principles of physics predict the existence of such hypothetical things, but no one has yet seen one. Black holes continue to pique the interest of scientists and astronomers as they seek to understand the nature of these mysterious cosmic engines. Please hit the like button and subscribe to our channel if you found this explanation of the black hole discovery helpful.